Boy, I better get to my computer fast so I can make that video. Whoops, I guess I was going a little too fast, but I'll make the video anyway. So we're going to, with this example, use Lagrange multipliers to find the dimensions of a rectangular box that's open at the top, so it doesn't have a top, but it contains 32 cubic feet of space, and here's the clincher, it contains the smallest amount of material for its construction. It's like if I was making it out of plywood, I'd be buying the least amount of plywood, or I'd be using the least amount of wood. So, quick look shows what we want to minimize. X, the way I've designed this is Z on this side, X on this side, Y on this side. So the bottom is X by Y. This side is Y by Z, and so is this one. So we got two of those. And this side over here is X by Z, and we have this one and the one in the back, so we got two of those also. So this is what we want to minimize, because we want to minimize the surface area of this box, subject to the constraint that X plus Y plus, or X times Y times Z equals 32. It has to contain 32 cubic feet. Well, del F, that's easy. Partial of this with respect to X is Y plus 2Z, so Y plus 2ZI. Partial with respect to Y is X plus 2ZJ. Partial with respect to K is, with respect to Z, my fault, is 2X plus 2Y. So 2X plus 2Y times K. And there's our del F. Now, this constraint, we could call it G of XYZ equals XYZ minus 32, but the partials would be the same, even if I didn't do that. So, partial of this with respect to X is Y times Z, and then we'll multiply that by lambda, so lambda YZ. Partial of this with respect to Y is XZ, and that's going to have a lambda attached. And the partial of this with respect to Z is XY, and that also has a lambda attached. And so we know that Y plus 2Z equals lambda YZ. We know that X plus 2Z equals lambda times YZ. So in other words, I think I just went there. Here, X plus 2Z equals lambda XZ. So X plus 2Z equals lambda XZ. And finally, we know that 2x plus 2y, our k component, is equal to this k component, so 2xy. Now, what does that give us? Well, solving this equation for lambda, we get lambda equals y plus 2z over y times z. Solving this one for lambda, we get x plus 2z over xz. And solving this one for lambda, we get 2x plus 2y over xy, so all these have to be equal to each other, and they're equal to lambda alike. So what does all of this mean? Well, if we put these two equations together, we would get xyz plus 2xz squared equal to this times this, so xyz and then plus 2yz squared. And the xyz happens to be the same on both sides, so we got 2xz squared equals 2yz squared. We'll cancel out the 2's, and we get xz squared equals yz squared, so cancel out the z squareds, we got x equal to y. If x equals y, then that was good to know. And we can do the same thing with I guess it's going to be this one and this one. So then I'd have xy squared plus 2xyz, see it? Equals this times this, so 2xyz plus 2y squared z I was going with this one and this one. I was mistaken. This one times this plus this times this. That's what I should be going with. So then I would have x squared 2xyz, x squared y rather, times 2xyz, and this one times this one will give me 2x squared z plus 2xyz, and then the 2xyz's on both sides cancel out. We can cancel out an x squared, so y equals 2z. So we got x equals y, y equals 2z, and because x equals y, therefore x equals 2z also. And z equals x over 2. Now I'm trying to think where I know that from. Well, I guess I knew that from this one by solving it for z. Okay, so I'm in good shape. So x, y, z, x times y times z equals 32 becomes x times x over 2 equals 32, so x equals 4. And hence, since x equals y, y is also 4, and z would be equal to 2. Hence, we can minimize the surface area of this box if we make it 4 feet by 4 feet by 2 feet high.